Hi, today we will discuss confidence intervals, or another term for the same thing, interval estimators. So estimators we have previously discussed were called point estimators. Why? Because when you solve an estimation problem, you get just a single number. So you have a parameter, you estimate it, and as a result you have an estimator, and this estimator is a number, and you say that this number is an approximate value of the unknown parameter. So this way of estimating is pretty good if you need to know this unknown value of the parameter to substitute this value to some formula. So if you need to know the parameter for some further calculations. But when you estimate a parameter in this way, you don't understand how accurate this estimator is. So you just have a number. You can say that so this is an approximate value of the unknown parameter, but you can't say so how accurate this estimator is. And if you are interested in accuracy of your estimating, it's better to find not the point estimator but an interval estimator, or a confidence interval. So how we define it? So we say that interval estimator, or a confidence interval of the level 1 minus alpha, or that is the same 1 minus alpha times 100% confidence interval for the parameter theta, is an interval with its endpoints being random and depending on the sample, such that this interval covers unknown parameter theta with given probability 1 minus alpha. So, for example, confidence interval of the level 0.95, or that is the same 95% confidence interval, is such an interval that is the interval that covers unknown parameter with probability 0.95. So with probability 0.95, parameter is inside the interval, and with probability 0.05, outside of it. So how can you understand accuracy of your estimating when you are using confidence intervals? You just hear the thing that shows you the accuracy is the width of the interval. So if the interval is wide, this means that this estimator is of low accuracy. If the interval is narrow, this means that estimator is of high accuracy. So, for example, if we apply this to an example I have already gave you, so I have a table and I measure the length of this table by multiple measuring it with a short ruler, as I have no measuring tape. So, and if I'm interested in point estimator as a result of my estimate, or when I solve the estimation problem, so I say that approximate length of the table is equal, the length is approximately equal to 190.2 centimeters. So this is the point estimator. And when I'm using a confidence interval, an interval estimator, I say that with probability 0.99, real length of the table is from 189.7 to 190.5 centimeters. So I give an interval, and so I can say that if the width of the interval is, I don't know, 2 millimeters, this is an estimating of very high accuracy. So if I can say that with high probability, like 0.99 or 0.95, actual value of the parameter is inside this very narrow interval of just 2 millimeters. This is highly accurate estimator. So if I say that with probability 0.99, real length of the table is somewhere from 160 to 220 centimeters, this is an estimator of very low accuracy. So because the width of the interval is very big. So a confidence interval shows us how accurate the estimator is. Unlike the point estimators for confidence intervals, we don't have a universal method, a universal algorithm to derive a formula for the confidence interval. So for point estimators, we have a maximum likelihood method that can be used to derive, to evaluate the formula of an estimator. Unfortunately, for interval estimators, we do not have such a method. So that is why we won't evaluate formulas for confidence intervals ourselves. I will only give you several typical situations when we use confidence interval. I'll show you the formulas and we will just look how to apply them to a practical problem. So let's start. The first type of confidence intervals that we usually use are confidence intervals for the expected value, for the mean value of a normally distributed sample. So the first situation is when you say that your sample x1 xn is normally distributed and you have only one parameter unknown. So mu is unknown and sigma is given. So the first situation is when sigma is given, and you can see the formula for the confidence interval of the confidence interval for mu. So here you see that you need sample mean x bar, the sigma that is given, that is supposed to be given, and the quantile of the standard normal distribution. But this is actually a little bit fictional situation when you know the sigma somehow. Usually you don't know the sigma, usually you have just the sample itself and nothing more. And you want to find confidence interval for the expected value when the sigma is unknown. So this is the second formula. So the second formula is the formula of the confidence interval in case of unknown sigma. So here you see that you need the sample mean, the sample variance. So Sn in this formula is the square root of the sample variance, and the quantile of the student's distribution. So this t of n minus 1 with index 1 minus alpha over 2 is the quantile of the student distribution. We have not discussed this distribution yet. Why? Because this is an auxiliary distribution, so it doesn't have any physical meaning. So no random variables, there are no random variables in our real life that follows this distribution. So we need the student distribution just to solve some problems in mathematical statistics, and the only thing you should know about this distribution is that there are tables of the quantiles of this distribution. So when you need the quantile, like here, to construct a confidence interval, you can open a table or you can Google just for a table. So table of the quantiles of the student's distribution, and so you will find the table and you can find the quantiles using this table. So these are confidence interval for the expected value. Another situation is when you have not a single sample, but you have two samples. And you are interested in the confidence interval for the difference in means. So the first sample has its own mean value, the second one has its own mean value, and you are interested in difference. The parameter to be estimated is μx minus μy. So μx is the mean value of the first sample, μy is the mean value of the second sample, and the parameter to be estimated is μx minus μy. And here we usually deal with two cases of this problem. The first one is when the samples are paired. Paired means that we measure some numerical feature for the same objects. Usually this is before and after. So x's, like for example, several people tried some diet to lose their weight, and x's are their weights before this, and y's are their weights after. Or some sportsmen tried a kind of a new training program to improve their results, and x's are results of these sportsmen before before completing the training program, and y's are the results of the same sportsman after the completing of the training program. So this means that paired sample means that these samples are actually observations of the same value for the same objects, but under different conditions. So what is to be done here? So the first step is to find the sample of differences. So di is the difference of xi and yi, and then after this everything is done like you are estimating just a single expected value, an expected value of a single sample. So you do the same as you have already seen, but for differences, for the sample of differences. So you calculate the mean difference, the sample variance of differences, and you construct the confidence interval using the quantiles of the student's distribution, just according to the same formula. Another important situation is a situation when these samples are not paired but independent. So this is a situation when x's and y's are observations of different objects. So, for example, you think that people in Moscow have on average higher salaries than people in, let's say, in St. Petersburg. And so x's are salaries of those who live in Moscow, of a random sample of people who live in Moscow, and y's are salaries of a random sample of people who live in St. Petersburg. So this means the samples are independent. So you observe, you choose random people in Moscow and you choose random people in Petersburg, and so they do not depend on each other anyhow. So this is not before and after. These are two completely different series of observations. And in this case, the formula is a little bit more complicated. So here you are to find x bar and y bar, so sample means for both samples, and then you are to find sample variance of the united sample according to the formula you can see, and then the confidence interval is constructed with the help of the two sample means, one sample variance of the united sample, and the quantile of the student's distribution with parameter m plus n minus 2. So another popular type of confidence intervals are confidence intervals for variance of a normally distributed sample. So we are usually interested in expected values and variances, in mean values and variances. So here I here you can see two formulas, and they describe the same situations as for the expected value. The first formula is for the situation when mu is given. So we want to find a confidence interval for unknown sigma squared, for unknown variance, in situation when mu, the expected value, is given. So the first formula, in the first formula you see that you need to substitute mu to the formula. And the second formula is for the case when mu is not given. Actually, this is what we usually have in real life. We usually have just a sample and nothing more. And so here you are to calculate sample variance. So Sn squared is a sample variance. And for both cases, you are to use quantiles of the chi-squared distribution. So chi-squared distribution is also an auxiliary distribution in mathematical statistics. So you don't, we did not discuss this distribution for the same reasons, so as it has no physical meaning, and you're just, you should know that there is such a distribution, and you can find the tables of the quantiles of this distribution. This parameter in brackets, both for the student's distribution and for the chi-squared distribution, the parameter is called number of degrees of freedom. So here you say that this is a quantile of the chi-squared distribution with n-1 degree of freedom. Or in previous case, there were quantiles of the student's distribution with n-1 degrees of freedom, or m plus n-2 degrees of freedom. So this term degrees of freedom is a little bit this is not so very good term, but so it has already become a traditional one. So that is why we don't say just with parameter n-1 chi-squared distribution with parameter n-1, we say chi-squared distribution with n-1 degree of freedom. So these are confidence interval for the variance of a normally distributed sample. So you can also compare two variances in a similar case to the one when you compare two expected values. So you can say that you have two samples, and your parameter to be estimated is proportion of two variances. So sigma y squared divided by sigma x squared. And so you can see the formula for the confidence interval. This is the situation of two independent samples. So what you see now is a confidence interval for the proportion of two variances, proportions of variances of two independent samples. And here you use quantiles of Fisher distribution, the third auxiliary distribution of mathematical statistics. So Fisher distribution has two parameters. They are also called degrees of freedom. So here you say that you need quantiles of the Fisher distribution with n-1 and m-2 degrees of freedom. So that is how we can estimate with an interval parameters of a normally distributed sample. Third important parameter that we are usually estimating with a confidence interval is a proportion or a probability. So, as you know, the proportion, population proportion, or a probability of a random event, this is actually the same. And the natural way to estimate unknown probability or unknown proportion with the point estimator is the sample proportion. So you repeat a trial, repeat an experiment, and you count number of successes, and then you divide number of successes by the number of repetitions of the experiment, and this is called sample proportion. And this is natural way to estimate unknown probability of a random event. And so if you want to use a confidence interval, if you want to estimate this unknown probability, not with a point but with an interval, so the formula is the one you can see now. To apply this formula, you need the sample proportion and the quantile of the standard normal distribution. So Z is the standard notation for the quantiles of the standard normal distribution. Last case we will discuss is the confidence interval for a difference of two proportions, or for difference of two probabilities. So this is a situation when you have two series of experiments, so and N1 and N2 are number of trials, so in the first series and in the second one. M1 and M2 are numbers of successes respectively, and so P1 and P2 are population proportions for these two populations, or probabilities of success for these two series of trials, and P1 hat and P2 hat are two sample proportions. And so you are interested here in a confidence interval for the difference of two population proportions, so for P1 minus P2, and the formula is the one you can see now. So here to construct this confidence interval, you need two sample proportions and the quantile. So these are the most frequently used confidence interval. I would say that 90% of all usage of confidence interval in our practice is covered by these formulas we have discussed today. So I didn't give you the universal algorithm to evaluate a formula for a confidence interval, but I gave you the formulas that cover 90% of all cases when you need to find a confidence interval.